Good morning, students. Good morning, students. So, in the last classes, we have completed our first unit of an operational amplifier, and second unit. The first unit is nothing but Opamp. We are going to study about the block diagram of Opamp, and in the second unit, we have studied about the characteristics, different characteristics of Opamp, that is AC characteristics as well as DC characteristics. And now, from today onwards, we are going to discuss about the third unit, that is operational amplifier applications. So third chapter is going to deal about the applications of operational amplifier. In this applications of operational amplifier, so operational amplifier is going to have linear applications as well as non-linear applications. So non-linear applications like comparator, we are going to observe the performance of comparator, and maximum we are going to discuss about the linear applications mostly in this chapter. So before going to the applications, once again we are going to discuss about the ideal characteristics as well as practical op-amp characteristics, and then we are going for applications. So first we are going to discuss about the basic applications of operational amplifier. So coming to the basic applications of operational amplifier, so here basic applications like Opamp, which is going to act as inverting amplifier as well as non-inverting amplifier, and it is also going to act as voltage follower. So these three are the basic applications of operational amplifier. First we are going to discuss about these three applications, and then we are going to next applications of operational amplifier. There are several applications regarding this operational amplifier. So in this we are going to discuss about amplifiers. The name itself, operational amplifier, is nothing but an amplifier, how it is going to perform its job as an amplifier, and then how it is going to generate the signals, so like oscillator, and then multivibrators, which generates a non-sinusoidal waveforms, and then operation means, as we have discussed in the first chapter itself, so it is going to perform mathematical operations like addition, subtraction. So how to perform addition, how to perform subtraction, and as well as how to convert these logarithmic values into anti-logarithmic values. So how to convert anti-log into log as an anti-log and log amplifier, and as a comparator, as a sine wave generator, square wave generator, Opamp as a rectifier. So all these applications we are going to cover under this chapter. So first we are going to discuss about the basic applications of operational amplifier. So coming to the basic applications, before going to the basic applications, so we are going to discuss about ideal op-amp characteristics. So what is an ideal op-amp, as we have discussed in the last class? So here you can see the operational amplifier block diagram. So here you can see the block diagram of operational amplifier in which Vi is the input signal, Zi is nothing but the input impedance, and Z0 is the output impedance, and this is the gain of operational amplifier AV, and V0 is the output of an operational amplifier. So how these characters will be for an ideal op-amp? So ideal means it is not existing practically. That means we are assuming that must be 100% perfect. So if we consider it as an ideal, then the input impedance of an operational amplifier must be infinity. Input impedance must be infinity. So such that the op-amp terminals does not draw any current. That means infinity means op-amp terminals is not allowed to draw any current. And coming to output impedance of an operational amplifier, it must be almost zero. There must be no resistance in the output side of an operational amplifier for ideal op-amp. So coming to voltage gain, that is open loop voltage gain. So open loop voltage gain must be as high as possible. As high as possible. That is what here it is indicated that AV is equal to infinity. And differential input voltage. What is the differential input voltage? Actually, when op-amp is given with a 2, that is Vi, is equal to 0 volts, then the output must be 0. But practically this may not happen. There are several factors. Due to those factors, the op-amp is going to have some voltage. So these are the ideal op-amp characteristics. So coming to this, input impedance must be infinity, output impedance must be 0, and AV is equal to infinity, that is open loop voltage gain. And if Vi is equal to 0, then V0 must be equal to 0. So these are ideal op-amp characteristics. So coming to the bandwidth. What about the bandwidth? So coming to the bandwidth must be also infinity. Why? So we are considering op-amp as a ideal one. Ideal one means ideal op-amp must perform its amplification, that is perform its operation from these operations same at 0 frequency as well as at infinite frequency. So because of this, op-amp must have infinite bandwidth. That means at any frequency, the op-amp must work in the same manner. And coming to the CMRR, common mode rejection ratio. So common mode rejection ratio must be also infinity. That means for an ideal op-amp, there must not be a CMRR. That means CMRR, if you consider CMRR, it must be infinity. Why? Common mode must not be there. That is, due to the common mode must not be there. So if common mode is 0, then you know that the CMRR is nothing but it is differential gain. This is a ratio of differential gain to the common mode gain. If common mode gain is 0, then what happens? The CMRR will be infinite. The CMRR will be infinite. In the same manner, the sleeve rate for an ideal op-amp. So the sleeve rate must also be infinite when we are considering this ideal op-amp, ideal operational amplifier. So in this manner, the op-amp must have different ideal characteristics. So ideal means it is 100% perfect. But practically 100% perfect thing may not be possible. So that is why we are going to here nothing but what our practically fabricated operational amplifier must possess the characteristics. So if we consider ideal one, so we are going to compare with that. So our op-amp, practical op-amp must be nearer to the ideal one. That means the op-amp is going to work like that. So this is how we are going to, these are the ideal characteristics of operational amplifier. And coming to practical op-amp characteristics, so here you can see practical op-amp. So practical op-amp is nothing but, so op-amp which we are considering, the op-amp which we are considering is nothing but the practical op-amp. So what must be, what are the characteristics, what are the different characteristics, how the different characteristics must be for this practical operational amplifier. So here you can see the equivalent circuit for an operational amplifier, that is practical operational amplifier. So Vi is the input voltage which is given to the inverting terminal as well as non-inverting terminal of op-amp. So Zi is the input impedance. So in case of ideal op-amp, so we have discussed that Zi must be infinity. That means when we are coming to practical op-amp, that Zi must be very, very high. That means it must be, as we have discussed that, the practical op-amp characteristics must be similar. That means must be nearer to the ideal op-amp characteristics. So that is why we are going to consider here input impedance in the order of high ohms. That is, here we have where we have kept that input impedance in mega ohms. And coming to the output impedance, in case of ideal op-amp, the output impedance is almost zero. It's zero, nothing but. So coming to the practical one, that means ideal op-amp impedance is zero, but practically it may not possible. If you are using a wire also, a conducting material also, that conducting material is also having some resistance, a low value of resistance practically. So this is how the output impedance of an op-amp must be a few ohms, which may not be equal to zero, but it will be very small. It must be very small. So coming to open loop voltage gain, so in ideal op-amp, we have discussed that open loop voltage gain must be infinity. So here, that open loop voltage gain must be as high as possible. So this is how we are going to consider the open loop voltage gain for an operational amplifier. And then some of the measures you have to take. That means some of the conditions will be there when you are choosing a practical op-amp. That is, input impedance must be as high as possible, output impedance must be as low as possible, and open loop voltage gain must be as high as possible, and coming to the output offset voltage should be as low as possible. Why? Because this output offset voltage is going to depend upon input offset voltage and input bias current. So these two must be very small. Then when those two are very small, and then output offset voltage must be also small. And the operating bandwidth, coming to the bandwidth must be as high as possible. That means Opamp must perform its function better at a maximum range of frequencies. That means if we consider from minimum range of frequency to maximum range of frequency, the operation of the Opamp must perform better. As we have discussed in our second chapter, the frequency response, the gain is going to fall at a higher frequencies where you have observed. That means the frequency response of practical Opamp will be around, it will be maximum at from 1 kHz frequency to 100 kHz frequency. So this we have observed in our practical Opamp, and this will be the bandwidth. So we have also discussed about how to improve this bandwidth of an operational amplifier, and coming to the CMRR, the common mode rejection ratio must be as high as possible. And coming to the slew rate, as you know, that slew rate must be for an ideal op-amp, the slew rate must be infinity. Here for practical op-amp, that must be very high. So these are the conditions we have to observe when we are selecting an op-amp for our application. So this is how we are going to, these are the practical op-amp characteristics. And coming to op-amp applications. So up to now we have discussed about the characteristics of op-amp, and then we are going to see the applications of op-amp. So the basic applications of op-amp, there are three basic applications of op-amp. This op-amp is used for linear applications as well as non-linear applications. So linear applications means op-amp is going to operate in a linear region. So linear region means, so the op-amp linearity means what? As we have studied in our, as we have studied, or you are going to study, you have studied in your pulse and digital circuit subject. So linear wave shaping. In that linear wave shaping, we have studied about linearity. So what is linearity? That means whenever, if you take any circuit or any device, whenever the input signal is going to change, the output must respond in the same manner. If the input is going to change, the output is also must change. The output must also change. So this is what the linearity. So the op-amp must possess this linearity when it is going to operate in a linear region. Next, non-linear, like the op-amp, which is used as a multivibrator. That is nothing but a clippers. Non-linear applications we have discussed there in the PDC. That is non-linear applications is nothing but this op-amp may also be used as a clipper, and also it also may be used as a clapper. So these are non-linear applications. So basically, basic applications. Today we are going to discuss about the basic applications of operational amplifier. So the basic applications are nothing but inverting amplifier, non-inverting amplifier, and voltage follower. Inverting amplifier, non-inverting amplifier, as well as voltage follower. So these three we are going to discuss in our today's class. First, we are going to discuss about the inverting amplifier. So what is this inverting amplifier? So why the name? Why it is named as inverting amplifier? So see here, this is a circuit for an inverting amplifier. So here we are giving the signal which has to be amplified to the inverting input of an operational amplifier. So here you have to observe that one thing, that is the input signal is given to the inverting input of operational amplifier through a resistor R1, and the non-inverting terminal of op-amp is grounded. So here you have to observe that thing, that non-inverting terminal is grounded, and inverting input, for inverting input we have given the input signal which has to be amplified, and then the feedback is provided with the help of RF. So why we are going for this feedback, you know that. So for operating this operational amplifier in a linear region, we must consider the closed loop op-amp. So for maintaining the closed loop, so we are going to use this feedback resistor. So this is the circuit diagram of inverting op-amp. So coming to the operation of this circuit, this amplifier, operation of this circuit, this op-amp is going to act as an amplifier, as well as it is going to invert the input signal. Invert means it is going to phase shift the input signal by 180 degrees. That means if you give a positive cycle as an input, then the output will be a negative cycle. So this is what you are going to observe in this inverting amplifier session. So coming to here, so we are going to discuss about virtual ground concept or virtual short concept. So virtual ground concept means, nothing but what is virtual ground? So virtual ground is nothing but, if you consider two nodes, the voltage at those two nodes, they are not connected. If you consider two nodes, they are not connected practically. They are not connected to each other practically. But we are going to assume that there is a virtual connection between those two nodes. Then we are going to call that as virtual ground concept. So virtual ground concept means nothing but here, as this non-inverting terminal is grounded, then we can say that the inverting terminal is also grounded. Here, this is the inverting terminal input. This is the node here. This node is also grounded. We are going to assume like that. That means this concept is nothing but virtual short concept. For an op-amp, the voltage at the inverting input terminal is equal to the voltage at the non-inverting terminal. So here, the inverting terminal voltage as well as non-inverting terminal voltage must be equal. And according to virtual short concept, the voltage at the non-inverting input terminal of an op-amp will be 0. So the voltage at this op-amp will be 0, according to the virtual short concept, as we have discussed now. So due to that, we can say that when this terminal is grounded, so the potential at this node is also grounded. So we are going to consider this node as V1. Let us consider this node as V1. Nothing will happen. So now we are going to write the nodal equation, that is KCL, nodal equation for this operational amplifier. So here already we know that here we are having 0 volts. V1 is nothing but 0 volts. As this is grounded, this is also grounded. Ground means nothing but ground is having 0 volts potential, and this inverting input is also at 0 volt potential. Then we are going to write the nodal equation from this point, from this node. So 0 minus Vi divided by resistance in this part is R1. So 0 minus Vi divided by R1, and plus next we are going to come this side. So 0 minus the voltage at this point will be V naught. 0 minus V naught divided by resistance in this part will be Rf. So 0 minus V naught divided by Rf, which is equal to 0. Which is equal to 0. This is nothing but case here. So we are going to write the current equation. So this is I and this is also I. This is the current flowing through R1 resistor and this is the current flowing through Rf resistor. So when we are going to solve this equation, so minus Vi by R1 plus minus V naught by Rf is equal to 0. If you bring this minus V naught by Rf to right hand side, this will become plus, and this is what the equation looks like. That is Vi by R1 is equal to V naught by Rf. Then bringing this Rf to this side, okay, what happens? V naught is equal to minus Rf by R1 into Vi. So coming to the gain, so V naught by Vi, we are bringing this Vi to this side. This will be coming into the denominator section, and V naught by Vi is equal to minus Rf by R1. So you can see here from these two equations you can observe that thing. So output voltage is equal to the multiplication factor into input voltage. So if this is 1, then output voltage is equal to input voltage. But in inverted position, you can see this minus indicates that the output has been inverted by 180 degrees. So if Rf by R1 is equal to 1, then the output voltage is equal to input voltage. If Rf by R1 value is equal to 2, then the output voltage will be doubled. The output voltage will be doubled when compared with the input voltage. So that depends upon that the gain depends upon these Rf1, R1 values. And you can see the minus symbol indicates that there is a phase shift between, that is 180 degrees phase shift between input and output. Input and output. So this is how this is the operation of our inverting amplifier. Opamp as a inverting amplifier. So when we give a signal, so then the signal, the output is going to depend upon minus Rf by R1 into Vi. So the output is going to be inverted, as well as the gain going to depend upon Rf and R1 factors. So this is the operation of inverting amplifier. Therefore, the gain of inverting amplifier will be Rf by R1, and negative sign indicates that there is a phase shift. So this is Opamp as a inverting amplifier. Next, we are going to discuss about Opamp as a non-inverting amplifier. So what is this Opamp and how it is going to work as a non-inverting amplifier? So here nothing but simply, so we are giving input to non-inverting terminal. Here we are giving input to non-inverting terminal, and we are going to make an inverting terminal to be grounded through R1. And we are going to make the inverting terminal to be grounded through R1. So here you can see we have given the input to the non-inverting terminal, and inverting terminal is grounded through R1. And as we know that due to virtual ground concept, as here we are having Vi, then here also we are having Vi. Here also this node also the potential will be Vi. So now we are going to observe how this non-inverting amplifier is going to produce the gain, and what will be the gain, and this gain is going to depend upon which factors we are going to see now. So coming to the operation, so here you can see, here we are having Vi. So from this node we are going to solve this equation. Vi, here we are having 0 potential. Vi minus 0 divided by R1. Vi minus V naught divided by R, nothing but, is equal to 0. Vi minus Vi minus 0 divided by R1, and V naught, sorry, Vi minus V naught divided by Rf will gives the which is equal to 0 will give the operation of this Opamp. And by solving that equation, you are going to get V naught into R1 divided by R1 plus Rf is equal to Vi. So by nodal equation also we can write this. So here we are going to consider Vi. So when we are going to write the equation for Vi, then we can write V naught, the other voltage source V naught into the opposite resistance, which is nothing but the opposite resistance for this, that is the shunt resistance for this V naught will be R1, and then V naught into R1 divided by total resistance in this path will give the Vi value at this node. From this also we can write, as well as we can write how we have written in the inverting amplifier. Inverting amplifier lo manam ela aithe consider chestunamo ala kuda raskochu. In the same manner we can write, no problem. So if you solve that equation, then we are going to get V naught by Vi is equal to 1 plus Rf by R1. So here you can observe the main thing is that the gain is equal to, so here you can see the gain is equal to 1 plus Rf by R1. So there is no inversion. The output has not been inverted. You can observe the thing that the output has not been inverted, but it is amplified. So then, then the amplification factor, so that is amplification is going to depend upon, again here, Rf and R1 values as well as plus 1. So if Rf by R1 is equal to 1, then the output will be doubled. If Rf by R1 is equal to 2, then output will be tripled. So like this, we are going to, the gain of the non-inverting amplifier is going to depend upon the same thing as well as we have observed in the inverting amplifier, depends upon R1 and Rf values. Same thing, R1 and Rf values. And this is how the Opamp is going to operate as a non-inverting amplifier. So again I will discuss this topic. So here you can observe that in a non-inverting amplifier, the input is given to non-inverting terminal of operational amplifier. So that is the positive terminal of an operational amplifier. So when we are considering this input here, then the voltage at this node is also having Vi. So now we are going to write the equation for this Vi. So for writing the equation for this Vi, then we can write a nodal equation like this: V naught, the other voltage source, that is V naught, into R1 divided by the total resistance in this path, R1 Rf plus R. So that is how they have written the equation for Vi. So then we are bringing this V naught to this side, or Vi to this side, and then bringing this to right hand side. So when Vi came to left hand side, it will be in the denominator, and when we are bringing this equation to right hand side, the numerator terms will become denominator terms, as well as denominator terms will become numerator terms. You know that. And the equation will be V naught by VA is equal to R1 plus RF by R1. And then, as you know that V naught by VF is VI is the gain of operational amplifier, and the gain which is equal to 1 plus RF by R1. So the gain here again depends upon RF and R1 values. So this is the operation of non-inverting amplifier. Operation of non-inverting amplifier. And then next application is voltage follower or unity gain follower. Okay, voltage follower or unity gain follower. The same thing as we have observed in the inverting amplifier. So the same thing as we have observed in the inverting amplifier, that is non-inverting amplifier, that is, so we have given input to the non-inverting terminal of Opamp. So here also we have given the input to the non-inverting terminal of Opamp. So there, and we are eliminating the two resistances. So RF is eliminated as well as R1 is eliminated. As we know that due to virtual short concept or virtual ground concept, so the potential, that is the potential at the non-inverting terminal is equal to the potential at the inverting terminal. That means the voltage at the inverting terminal is nothing but VI. So from that we can say that VI is equal to V naught. VI is equal to V naught. That means output voltage is equal to the input voltage. The output voltage is equal to the input voltage. So here you can observe in this diagram, circuit diagram. So the input is given to the non-inverting terminal, and then the output is directly fed back to the inverting terminal without using any resistor. So that means by virtual ground concept, here the voltage at the non-inverting terminal is VI, then the voltage at this node will be also V. So here there is no resistance. We can say that VI is equal to V naught. VI is equal to V naught. So this is nothing but a buffer amplifier, unity gain follower, voltage follower, so which is going to produce the same output voltage as input voltage. So same output voltage which is equal to the magnitude of input voltage. So these three are the basic applications of operational amplifier. So in the next class we are going to discuss about next topics, next applications we are going to discuss in the next class. Thank you, students.